Hi, I'm Samir Shende, and I'll talk about the Tau performance system. Since this is a hands-on workshop, here is how you use Tau. You take an uninstrumented application running on Polaris, running on other systems. You just load the Tau module, and you launch it with a tool called Tau exec. It takes many parameters. You can specify the use of CUDA. You can use parameters like level 0 for Intel GPUs, event-based sampling, and then it generates performance data that you can view in a tool called paraprof. So that's the gist of the tool. It's a profiling and tracing tool. So you can see detailed information about what your application is doing. There are many ways to insert hooks in your code. One of them is just to launch it with an uninstrumented binary. But you can also rewrite the binary and instrument all the functions using a package called Dynast API. I'll try to show you some examples of different ways of adding hooks to your code. But the key takeaway is that whether your program is written in Fortran or C, C++, using DPC++, Python, or many other languages, you can automatically instrument the code. You can use instrumentation at the level of different runtimes, whether there is MPI, OpenSHMEM, and other GPU runtimes. ROCm is supported. We support level 0, DPC++, SYCL. We also support CUDA. And you can insert hooks in GPU programs with no changes to your binary. So your source code remains the same, your build scripts remain the same, your application binary remains the same. You just launch it with a command. You can rewrite it, you can launch it with the Tau exec command, and then run the application called paraprof. It tells you how much time is being spent in different code regions, even at the function level, even at the statement level. You can see how much time your application took. Instead of time, you can replace it with hardware performance counter data. You can see the time spent in barriers in MPI collective operations. How much time is wasted in those barriers in MPI all-to-all, for instance. You can see the time spent in different GPU runtimes, the memory usage, the energy, IO, even how the application scales. So the tool to use is Tau exec. And once you use Tau exec, you can enable different options, whether it is to see OpenMP performance data with OMPT or IO or memory data. And this is how you use it. You say Tau exec, and then you can specify a given configuration with a tag like rock profiler for ROCm. And you can say -L0 for level 0, kubectl, OpenCL, OpenACC. All of those programming models are supported, and event-based sampling, where it periodically interrupts your code and shows you at the statement level how much time is being spent in different code regions. If I configure Tau with a certain set of parameters, it makes a stub make file in an architecture lib directory which specifies those tags. And it's the same tags that I specify with the -t argument. So I can say -t kubectl, which stands for CUDA Profiling Tools Interface, or show me how much time is being spent in the GPU runtime. So this is, we have an example, a workshop, and you can see that information over here in this workshop directory. You can launch a node on Polaris, say, and since this is a hands-on workshop, what I will do is I will use module load Tau, and then I will build a code with CUDA. In this case, it's using the NVCC compiler along with the FTN compiler. It builds it with MPI. So there's MPI, there is CUDA in your application, and then finally it creates a bin directory. It puts all your binaries in there, and you just launch the application using app run with the uninstrumented binary. And here is the run.sh. I have loaded the Tau module so that the Tau exec is in my path. I'm saying -t kubectl for the CUDA, and then enable kubectl as well as event-based sampling in this code called tleaf. So normally I would run it like this. but now I will run it with this run.sh script, and it will run the code. As it's running, the hooks are being inserted in the CUDA runtime. With no change to the binary, we can then see how much time is being spent in different code regions. Now, I mentioned that we also support other GPUs, including AMD GPUs as well as Intel. And I'll show you an example of using tau on the Ponte Vecchio GPU. The Intel GPU is at the University of Oregon, and I will show you an example over there as well. Here, after the code completes, I'll get profile data. I can pack them in a PPK file, a packed profile format, and then with paraprof installed on my laptop, I'll bring this file over, I will view it. If I want to use the text browser, there's a tool called pprof, and I can also see that data over here. So now you can see pprof can be used right here, and you can see how much time was spent in different parts of the code, and how much time was spent in the collective sync operation. This is the time spent wasted in a barrier. And you can see the device to host and host to device data transfers. You can see the actual kernels executing on the GPU. So I can say paraprof, pack the file and put it in a directory, put it in a file called say t1.ppk, and it packs it up. And on my laptop, I can say scp from Polaris ppk directory t1.ppk and paraprof t1.ppk, and then I'll be able to see what's there in this file and see all the data in this. These are the kernels running on the GPU. Let me quickly show you an example of a configuration on a on a Intel GPU. If I say CLN4-L, you can see this is the data center GPU Max 1100. I can say build CMake, build this level 0 example. And if I say ZEGEM, say 4096, it runs this application on the GPU. You can see the Intel data center GPU Max series 1100 for the Ponte Vecchio. Now, if I want to use tau, I can just say tau exec with -t level 0. If it's not MPI, I say serial -L0, and then I can run the same code like ZEGEM 4096. And it runs this, and I can then see the output with say pprof. And here you see the gem is taking 868 milliseconds, and it's taking so long. And if I run this with a bigger, say 8192 by 8192, and it's now taking say 2.8 seconds for each iteration, then I will be able to run pprof over here and show you that this took 11.6 seconds total over 4 iterations. Now I could do something interesting. I could just take this ZEGEM binary and let me just say tau run with the same level 0 serial and rewrite this binary. Yes, I can take this ZEGEM and rewrite it as ze.i. So every function entry and exit gets instrumented automatically with tau. And then I will get this new binary where I have hooks at the function boundaries. So now if I run this code again with tau exec, instead of ZEGEM, let me try ze.i. with 8192. And I'm using Dynast API now. I will rewrite this. This is a rewritten binary, and it's running on the Ponte Vecchio GPU. So I have instrumentation at the CPU side as well as the GPU side, and I can see the functions like these. All of these functions that took place on the CPU side instrumented with tau. So all of these level 0 routines on the CPU side are there. I see the GPU functions. I can even go one step further and say, along with level 0, I want event-based sampling. So it goes down to collecting samples along with an instrumented binary, and I can get instrumentation at multiple levels. So whether it's MPI, level 0, event-based sampling, or rewriting the binary, it all works together with samples being collected. And so you can see which library where the samples were collected in the source code. Over here, there's a sample and so on. And these are the level 0 routines. So with this, we have a session going on later this afternoon in 1406. Please join me. We'll work on getting tau installed on maybe a different system that you may have in 1406 breakout session, or instrumenting your application. I'm also here tomorrow, and I'll be available after the workshop as well. So thank you very much.